talk about uncertainty in human-centered robots. Is that right?
That's correct. Thank you. Thank you. It's uncertain. It's been uncertain until the last minute. All right, well, thank you so much for inviting me in beautiful Singapore. Due to trends in my lab out of my control and therefore uncertain, I chose to talk today about uncertainty precisely. And I will start some of snippet thoughts about uncertainty. Uncertainty corresponds to the difference between our models and reality. Dealing with uncertainty requires contemplating the identification of model sets as opposed to nominal models to approximate the true plant at different regimes of operations. Noise is not uncertainty since it's stochastic in nature and unrelated to the input. In some microsystems, nonlinearities are often approximated by LTI systems, and uncertainty is mapped onto practical algebraic structures. Think, for instance, of disk or an Nyquist plot as a model for uncertainty, for the sense of uncertainty. Therefore, the control design problem seeks to stabilize every plant belonging to the entire model set. My student Greg will actually, I'm going to do a flavor of the talk where my students are going to talk a little bit, and he will talk in detail about what I'm talking about these types of uncertainties. I once told my students to perform a square shape using one of our SIA robots, Dreamer, and the results were quite poor. At NASA with Valkyrie, we were confronted with latencies on the Cartesian feedback controllers yielding similar poor results. We increasingly rely on centralized generic PCs to perform closed-loop controls, often suffering from real-time uncertainty. And we are there to incorporate new types of actuators such as Sears elastic actuators, SIAs. The cumulative effect of uncertainty, communications, and force control is a daunting challenge for controller design. This explains the reasons why many people convert computer torque controllers into joint velocity commands via admittance transformations, for instance. Indeed, embedded joint feedback controllers provide super-fast joint velocity feedback effort, which is key to achieving high-stiff behaviors. Separately, when using SIAs with force feedback, it results in a significant reduction of position control time. We have investigated many of those problems over the last couple of years and explained the difficulties with uncertainty, latencies, or controller tuning, especially on SIA systems. And here are just a bunch of them: optimal feedback control selection for SIAs, stability of performance limits, latency-prone distributed feedback controllers, a closed-loop solution for selecting maximum critical time to impedance parameters. Tuning is a difficult problem, there's no question about it, and SIAs doesn't make it easier. Anecdotically, my lab started working on RoboCup at Home 2017. Anyone here in the room working on RoboCup at Home 2017, going to Nagoya soon? Yes, I know you are. All right. So, to my despair, the student choice was to avoid Cartesian feedback control, not even visual servoing, and instead relying on a kind of initial localization and running sampling-based methods like RT or PRM, and then going to joint impedance controllers, joint position controllers. When asking about the motivation behind these decisions of my own students, as I said, they replied that they didn't want to spend time performing gain tuning and measuring of the communication latency. So I think I had to talk with Jae-Hong Park over here that tuning is a showstopper by now, and it prevents a lot of Cartesian core-body controllers and so on to progress at the level that we're seeing in sampling-based methods. So something to think about. And as I said, I was in despair, I'm still in despair. Nonetheless, I love SIAs elastic actuators for their reachability capabilities, their force sensing, and impact protection. And my interest within this domain are on providing agility to systems with high payloads. I'm interested in the upper spectrum of payloads. Maximum payload, what kind of agility we can achieve there instead of smaller loads, smaller systems. For example, we are now involved in the design of an efficient exoskeleton that can do a keg tossing. Keg tossing is this lumberjack sort of thing that you lift a big barrel as high as possible. And that requires high payload, a lot of dynamics, kind of things that I'm interested about. So, yeah, some of my interest. Last year, my student and I co-founded a company, Apptronic Systems, focusing on R&D for human-centered robots and providing high-power density CS with our electronic Taurus systems that, anyway, its commercial front is selling well. Shouldn't say it's good, but that's the truth. And to deal with high loads, we have been exploring thermal control by liquid cooling systems and thermal control. That's one of the areas we're focusing quite a bit now. These technologies were recently integrated into the Quario system. It provides excellent power density and efficiency, displayed here. To maximize the impedance switchable region, we incorporated viscoelastic materials for the reasons we explained before, not to deal with latencies. It's better to have the damping at the actuator level, which reduce the negative effects of the damping feedback control. And we are paying close attention for real-time uncertainty by careful design of communications and the end-to-end medulla system for our actuator series, real-time controls. Overall, this line of research is aimed at a new generation of efficient humanoid robots with high performance exoskeletons that we are excited about. And I want to stop my part. I want to invite my students, as I said. So in conclusion for this part, uncertainty and robustness are fascinating and important focus of my team. And Gray and Dokyun will add their beat and kind of the technical difficulties behind uncertainties in two different domains. So go ahead, Gray, please.
All right, thanks, Luis. So this is work we've been doing specifically to deal with the uncertainties in feedback controllers to model the plants we're doing feedback control on as model sets in a way that's based on data. So in the state-of-the-art method for H-infinity control, we basically have magically gained knowledge of what the plant is capable of doing. And there's not really a great justification in existence for how you can come up with this, deterministic bound on anything the plant is capable of doing. I mean, it's like knowing everything in the future about what your plant could potentially do. And a lot of the times it's really transparently heuristic. Like if you're using E as identity and J as some scaled identity, that's something you've made up. Although there are better, more reasonable things, they're still kind of fundamentally not based on data because, for example, the prediction error covariance approach from prediction error identification theory, that estimate of error, that covariance, gets smaller forever. The more data you get, the less uncertain your plant is. But really, your plant has some kind of variability that's natural. So we introduced this model to explain this. So our condition group model in the bottom is closely related to the linear parameter varying model, but it differs kind of subtly. So the LPV model is state space, and we're thinking about it more in the frequency domain. And in the LPV model, you explicitly model the influence of the parameter vector on the state space systems. This is the model that they use to justify gain scheduling, right? So the parameter vector to state space system relationship is how they determine the gain schedule. But what we're doing here is we're saying there's a condition vector C that determines the realization of the transfer matrix. And we don't know the relationship, we just know that unique condition vectors give some kind of deterministic result, and we bound the influence of the condition vector on the transfer matrix. And then one final quirk is that we allow the input phase review to be a part of the condition vector. So this means that we expect some nonlinearity due to the input. If we've got a backlash or something, then small inputs won't necessarily produce the same results as large inputs. So that's what we're trying to model here. And some notation, we collect the tests that have the same condition vector into condition groups. And each condition group has an average. And we can describe the variance within a condition group as the deviation relative to the average. talk about between group, the variance between the groups as the relationship of those averages to some best fit linear model, which is kind of mean-like if you think about the way you generated that model. So our identification approach uses sinusoids, explicitly sinusoids, and then casts the output of the system as a sinusoid of the same frequency as the input sinusoid. This is like a single period inverse discrete Fourier transform to get the output phasor. And if each pair input output as vectors is like a point in high dimensional space, and linear models are like hyperplanes in that high dimensional space. And what we've found is that the data does not really fit on a hyperplane. This is kind of fundamental. If we want to learn about uncertainty, and this is our novel technique for measuring systems in a way that shows uncertainty, it's pretty important that it shows non-linear behavior. So this is how we show that it demonstrates non-linear behavior. This is experimental data from a series elastic actuator, and we model the series elastic actuator as two inputs, a current and an external force, and we actuate them independently by having a second actuator that pushes on the series elastic actuator. And then the outputs are the motor position and the spring deflection. And the plot on the left is showing, I think, for the motor position, the expected data based on the best fit linear model in blue, and the output data. And what's clear about this is that they're both tightly clustered, and they're definitely not the same cluster. So it's a graphical representation of the fact that the within group variance is small, and the between group variance is very large. Now this corresponds to a statistical test that we did, an analysis of variance. You're familiar with statistics, and what we're plotting over here is this variance ratio, the estimate of the total variance of the noise. If it was a linear model, that's our null hypothesis, that it is a linear model. And the ratio of those two variance estimates, which should produce the same thing, so it should be 1. Notice this is a log plot. It's astronomically high. So it's like really, really clear that there's real data here that contains information about the uncertainty. So if we interpret this uncertainty geometrically, and we're trying to think about what the H-infinity model is geometrically, then in this high-dimensional space, it's a degenerate quadric, which is like a 5 minutes. Oh, shoot. So, yeah, it's a degenerate quadric, which is a cone-like shape. So to make this problem convex to identified models, we've reformulated the initial matrix into this second thing. And we do convex optimization by determining this matrix M and producing some potential benefits for automatically tuning gains. I'm so sorry, Don.
No problem. we still have 12 minutes.
We do?
Yeah, we were allocated 45 minutes.
Oh, okay. All right, but it's still, if you have questions, there'll still be time later. So Don Hume's going to talk about his results relating to uncertainty in humanoid robotics.
Okay, I'm Dong-Hyun Kim. Let me talk more about the high-level controllers such as full-body control or motion control, or motion plan. So we, like people in this room, believe that we can achieve the most dynamic and robust whole-body control by exploring the various algorithms. So the research objectives can be summarized in 3 words: agility, robustness, and projectability. Let me talk about the whole-body control first. So I would like to give a brief introduction of the whole-body operational space control, which is the whole-body control developed by Recentis. As you already well know, we start from the projecting the multibody dynamics to the contact constraints, which is defined with this equation. can find a task force provided between the unit velocity and operational space velocity. In this video, we're gonna control the two positions of the now. And at least it make it succeed to control two position. And then we added some functionality in our full body control framework. And one of them is the centroid angular momentum test. Here, in this video, you can see Valkyrie shaking the hand to counteract to the body rotation. But with the same test, but different hierarchy, the Valkyrie fixed the arm in the initial posture. To enhance the balance capability, we also made a capture point control task. To find the proper task input, we proposed a new simplified model, so-called input model. It turns out the dynamics are identical to the linear inverted pendulum dynamics. And this is controllable of the center of pressure to let the current capture point convert it to the desired location. And this is the central mass task input, resulting the capture point feedback control. This is a demonstration of the proposed balance control. We test our balance control both in simulation and actual systems. Indeed, implementing whole body control and test balance control in actual system is really difficult. More technical details and the result, you can find it in this paper. So last year, we found the problem of the whole body operational space control. This is a gazebo simulation, and Valkyrie just literally cannot stand up. So with a different task setups, it sustained the balance longer than that, but eventually click the foot and then falls off. So violation of the contact constraint causes these problems. The acceleration of the contact point is not zero, but rather than zero, which means that robot only can push the ground. To solve these problems, we incorporate quadratic programming formulation. In these quadratic programming formulations, there is the inequality constraint addressing the friction constraint on reaction forces. To compute the reaction forces, we need to specify the centroid momentum task first. And this centroid momentum task is one of the tasks in whole body locomotion control. The equations show how we stack the prioritized task. Whole body operational space control execute the multiple tasks by projecting the task force to the null space of the higher priority task. Instead, whole body locomotion control build a hierarchy in joint acceleration. Building task hierarchy in configuration space is not new, but we enhance the computational efficiency a lot by computing the velocity related term in configuration space instead of the operational space. And the last step is to find the torque command with calculate the reaction force and joint acceleration. So far it's about the whole body control, and let's talk about the motion planner. We designed our working planner based on the page space planner. The page space planner generates the working pattern based on the central mass pattern of the prismatic inverted pendulum model in phase plan. As you can see here, COM path looks like a connected parabola in sagittal plane. In frontal plane is similar to the semi-periodic parabola forming the closed cycle. So original algorithm is for straight walking, but with a small modification, we can steal the direction of the walking. When we want to change the direction, we align the orientation of the next local frame to the direction we want to go, and project the current state to the next local frame. As we show that we can do complicated working patterns with this method. We are preparing, actually, we developed the reinforcement running-based page space planner. We cannot cover all the technical details, but we want to show some result. In this result, this is a COM path according to the corresponding to the different policy, and pink line is corresponding to the final policy. As this iteration goes on, the policy, the performance of the policy is enhanced. With this policy encoded in the neural network, we do some replanning algorithm, and it enhances the robustness of the locomotion a lot. This is the demonstration for the push recovery, while it taking a step, we push it, the bike with a different direction and different impulse force. There's 300, a little more, different direction. But overall, it sustained the balance about to the external impulse, 350 to the 450. Okay?
That's it. Thank you very much. Easiest way to use a student for giving my talk.
So thank you, Luis. Do we have any questions?
Think about these answers. One party.
People are tired. No question? Okay, so let's call it for today. Let me conclude by thanking Dimitrios for the wonderful organization of the workshop, and also Morris and Ioannis, who's not here, and Ichi, or you see. Okay.
Thanks all for coming, and hopefully you enjoyed it. Prisma.